Hello. This is a presentation of, I guess recording is started. So we are group 11 and our topic is molecular origin of nonlinear optical responses. Here we will review some of the simpler approaches that have been implemented to develop an understanding of nonlinear optical characteristics of a various materials. Many of these approaches are based on the optical properties at the molecular level. And also here we will do a brief discussion of nonlinear optical characteristics of conjugate polymers, chiral molecules, and liquid crystal. So let's start with the first topic, which is a nonlinear susceptibilities calculated using time-independent perturbation theory. We are using time-independent perturbation theory as it is easier to implement as compared to time-dependent perturbation theory. And here our goal is to find how material responds to an intense laser light when the laser frequency omega is much higher than the natural frequency of omega naught of the material. We are taking as such because we want to avoid any kind of absorption losses. Okay, now let's dive into the derivation. So we are starting with the formula of energy stored in a material due to its polarization. So we know that this is the formula of energy stored uh, uh, as a function of polarization of a material at a particular value of tilde E. And now let express polarization in terms of susceptibilities. So this is how we represent. Now we'll put this value of P into the uh, this above example of energy stored, and we get this. And we know that W as a power series or in E, so we can determine susceptibility as such this n minus 1 ordered susceptibility equals to n minus n W and upon epsilon naught and ETH, like ETH, nth electric field, nth term electric field. And also, instead of using power series, we can also obtain this through the differentiation. For that, we need to differentiate W with respect to the E, and this we are differentiating it for the n times. We get this. So before going further, let's see a simpler example. So first we will see the hydrogen atom, like what happened with the hydrogen atom when high electric field is applied. So when we applied electric field to hydrogen atom, the energy of the atom's ground state, the lowest state of the hydrogen atom changes. And these changes can be denoted as omega. And this formula is, we can find this from the Stark effect. Omega, uh, omega can be calculated as a series in term of the strength of applied electric field E, and from the Stark effect, as I said before. And this is the formula. Here we know that the R is the Rydberg constant, and EAT is the atomic unit of the electric field strength. Now, we now take W as given by W n into the omega, which is n is the number density of atom, and we will introduce this formula into the above which we got here. Yeah, here which we got here. We'll introduce that into this formula. And from there, we can get the psi1, which is equals to n alpha, and alpha is equals to 9 upon 2 a naught to the power 3. And we can get uh, gamma, which is this. And the third order susceptibility is equals to n into the gamma. And here we know that a naught is a Bohr radius. from this standard scaling law, we can confirm that the alpha is like approximately like we can say proportionate to V, and gamma is proportionate to V to the power 7 by 3. And here V is the atomic volume. So now we see now let's move forward. Now how we'll see what the general expression of for the nonlinear susceptibility in quasi-static limit. We have seen for the hydrogen, which was a similar. So what we do for the other atoms or molecules rather than a hydrogen atom, we take the quasi-static limit. Here, like the problem in the quantum mechanics that it involved the energy state side of the atomic system, and whenever the electric field applied to it, it modified due to the perturbation. We know that perturbation. So it modifies whenever any electric field applied. So solution, what is the solution? What can we do? So we can, here we will use Hamiltonian. So we will assume that the Hamiltonian of the atomic system, which is represented as a sum of two terms, which is the S hat naught, which is represent the total energy of the free atom, and there will be a V hat, which represent the quasi-static perturbation due to external electric field. And here, as we say that the V hat is specifically related to the applied quasi-static electric field, that tilde E. And I have here shown that the electric dipole moment will be like this. Nu hat is represented as nu hat equals to minus E multiplied by E hat, and V hat as equals to nu hat multiplied by tilde E. Tilde is like quasi-static electric field which you have externally applied due to the external electric field. The atomic system's wave function is described by the time independent time independent Schrödinger equation, which I have given here. And to solve this energy and the state vector will represent as a powers series in term of perturbation, which I have given already. And here I have provided the first four order of energy due to the perturbation. And we can see that the omega G is the ground state, and S is another state, and T is another. Now to simplify this expressions which I have shown up above, we can use unsolved approximation which entails that replacing the resonance frequency, which is omega SG, by some average transition frequency. So we'll take some average, which will be average of all these omegas we have of the different state, and we can find the formula turn out to be like this. And also this summation of this becomes 1 due to the closure of quantum mechanics, and we can find very simpler formula which is given here like this: alpha equals to 2 into e to the power upon the h bar omega naught square equals to this x square. And this result shows that the linear susceptibility is proportional to the electric quadrupole moment of ground state electron distribution. This shows that. And for the second and third order susceptibilities, here I have given for that also. And this suggests that the linear and non-linear polarizabilities increases rapidly due to the with the physical dimension of the electron cloud associated with the atomic ground state. And this beta and gamma are called hyperpolarizabilities, and these are interrupted as a measure of higher order of moment of the ground electron distribution. Okay, so gamma is expressed in term of dimensionless quantity g, which is known as kurtosis. And here I have provided uh, how gamma is related to g. The gamma equals to alpha square g upon h naught h hat omega naught, and the g is equals to this. And the average transition, if we take like average transition frequency omega naught is related to the moment of the electron distribution. And we can use that to simplify. Like we can start with Thomas Reed-Spoon sum rule that state like this. And now we can use this further to simplify. Here we can, from using this, we can get the value of omega naught values, and we can find very simpler value of alpha, beta, and gamma. And I would like to clarify what alpha exactly is. Alpha is a measure of electric quadrupole moment of ground state electron distribution. Beta is the measure of octupole moment of the ground state electron distribution. And gamma depends on the both hexadecimal pole and quadrupole moment of the electron ground state electron distribution.
So today I am going to delve into like the fascinating realm of nonlinear optics, and I am going to be focusing on some of the semi-empirical models of nonlinear optical susceptibilities. We will use these semi-empirical models to predict some of the response and some of the quantities of nonlinear optics. So we will start by a generalization of the Miller's rule to the third order susceptibility. So here we are, you can see like we are using the first order susceptibilities, and we have we have like extended the expression to a third order susceptibility. And here we have to notice that omega 4 is like the sum of frequencies, and here A is like a frequency independent quantities that is nearly same for all material. And the drawback of this generalization of the Miller's rule is that it only holds for ionic crystals. Now we will be discussing on another like semi-empirical model, which is like the Wang's relation. Wang's relation is formulated by looking at the response near the quasi-static limit. So it in this like the third order optical susceptibility is directly proportional to square of the first order optical susceptibility, and we have a term q dash, which is given by g dash by n effective into omega 0. Here omega 0 is like the average transition frequency, and n effective is given as the product of the molecular number density n and the oscillator strength f. And g dash is like from the kurtosis of the ground state electron distribution. So this holds for both ionic crystals and at low pressure gases, where like the generalization of the Miller's rule breaks down. And now we will be discussing on another model of like bowling, glass, and Ovium. Here they have decided to extend like the nonlinear refractive. They are going to predict the nonlinear refractive index constant based on the linear refractive index constant and the linear properties. So we will get like we have expressions for the linear refractive index from the Lorentz law as well as the Lorentz oscillator model. The Lorentz law gives us this expression, which in which n is like the linear refractive index, and this expression is from the Lorentz oscillator model. So these two equations can be related, and here omega 0 has to be noted as like the resonance frequency. And by plotting refractive index as a function of frequency, here we will be able to get the effective number density n, like effective number density n effective, which will be like the product of like the molecular number density as well as like the oscillator strength, and also we can get the resonant frequency. So we have omega here is like the damping term, and like these are the equations we will be able to we have like come to using the Lorentz law and the Lorentz oscillator model. And like we on simplifying these expressions, like we have some common terms. On substituting them, we will arrive at this expression for n2. And experimentally, we have found that GF is approximately equal to 3, and it is found like empirically, like to many materials have come up with the same value for GF. And this is a graph for measured nonlinear refractive index and the calculated nonlinear refractive index. You can see like there is just a small difference in the values, and these are mostly ionic compounds. So there is only like a slight deviation, and it is almost following. There is no it's just a like a slight difference in value, but there is no like the graph do not seem to be deviating much. And now we will discuss another topic, which will be like the nonlinear optical properties of conjugated polymers. First of all, what are conjugated polymers? So they are like organic compounds, and they are polyunsaturated organic compound, which means they have the presence of a double bond, and we have at least more than one carbon, and they contain at least 3 alternating single bond and double bond. So when you have alternatives like single bond and double bond, this results in an interaction known as conjugation, which gives some unusual optical properties. So an example for this is PTS, which is a type of polydiacetylene, whose like third order susceptibility is so much higher and very significant as compared to like a normal compound like carbon disulfide. So here is a structure of polyacetylene. As you can see, there is alternating single and double bond. Like this can extend as like long chains, hence the abbreviation N here. Polyacetylene is like a chain like conjugated polymer. Here we can like these are some of the representations of like polyacetylene compounds, and we can see like the same compound can be represented in any of these two ways, and it would not be wrong. So that is where that leads to some interesting properties, which we will see. And we can see the pi bond um, is like away from the what do you say, the molecule, and it the electron cloud of the pi bonded electrons are away, and hence they'll be more free to move as compared to sigma bond. So in a long chain, this is how like the electron clouds will seem. like in two dimension. Um, so we can see a pi bond is usually formed by like the sideways overlap of two p orbitals, and like we can say like the sigma bond is always formed axially, like in the direction of approach of the two molecules, but pi bond is formed like perpendicular to that plane, and it is a weaker bond. That is why it is a weaker bond. So the optical response of these these such molecule which has like these delocalized, or what do you say, delocalized electron can be like it is very significant from that of like normal compounds, um, and especially if it's conjugated. So like the delocalization of pi electrons, as you can see, like um, see, if we number all the electrons, right, when the atom is like in conjugation, the pi bond can form to the left or the right, and it would not matter. Hence, there is like this arbitrariness in polymer chain representation, which leads to like a free movement of the pi electrons. So we have to now create a model for these pi electrons. So we are assuming them to move entirely freely, okay, in like a one-dimensional square well potential with length corresponding to polymer chain length. So from that we have equations for linear and third order polarizabilities given by this. Here we have to note their like how they are proportion to like the polymer chain length as well as the number of electrons per unit length. The third order polarizability is directly proportional to like fifth power of the length, which is very significant. And now we will try to form like the we will try to show this in experiment. Experimental results confirm this, okay, that like the fifth order of the length of the polymer chain is dependent on the hyperpolarizability. Hyperpolarizability is like the difference like from ground state to excited state of like a molecule, like the difference in like their optical property. And we can see that like as the chain length increases, like its fifth order, since it's fifth order, like the optical susceptibility increase very rapidly. So here we can see in the graph that according like dependent as the number of double bond increases, the optical molecular hyperpolarizability also increases, and optical hyperpolarizability also increases, and the as the number of double bond increases, so does like the delocalization, that is the electrons are more free to move around, as well as the length of the chain would also be higher. Hence like the molecular hyperpolarizability is also increasing. Now we are applying there is like this very interesting example of like C60, which is also known as Buckminster fullerene, which is like a which is you can see like its unique shape. It also has alternate single and double bond. In this, the electrons are free to move around the surface of the sphere created by this unique structure of the material. Thank you.
Hello, my name is Anil Roshan, and I'm going to be explaining about the bond charge model of nonlinear optical properties. So imagine you have a bunch of individual atoms floating freely. When they are on their own, it's easiest to understand their behavior using their own energy states or how their electrons move around. Now picture these atoms forming a crystal, where they are all arranged in a neat, repeating pattern. In this crystal lattice, the electrons on the outer parts of the atom act like they're stuck within the bonds that hold the atoms in their positions. We don't need to worry much about the inner electrons because they are tightly bound and don't affect how the crystal responds to light. In summary, when atoms are on their own, we look at how their energy states influence their behavior. But when they are part of a crystal, we focus on how the outer electrons are confined within the bonds of the crystal lattice. This helps us understand how the crystal reacts to light and other influences. Scientists have also determined higher order polarizabilities, which means they have studied not just the basic response, but also more complex behaviors of these bonds when exposed to electric fields. Even if there are other bonds nearby, each bond's response is predictable and doesn't change much based on its neighbors. This predictability simplifies our understanding and helps scientists design new materials with specific properties like how they respond to light. So, the susceptibility of a complex system can be predicted by summing the responses of the various bonds present in the material, taking proper account of their orientation. Hyperpolarizabilities can be determined either experimentally or by one of several different theoretical approaches. The figure above represents the bond charge model. Here, in the bond as an idealization, with, the bond is considered to be point charge Q, which is located between the two ions A and B. Here, Ra and Rb are the uh, covalent radii of A and B, and the bond length is the sum of Ra and Rb. According to Levine, the bond charge is given by Q is equal to E and V whole multiplied by 1 by epsilon plus Fc by 3, where Nv is the number of electrons per bond, epsilon is the static dielectric constant of the material, and Fc is a parameter known as the fractional degree of covalency of the bond. Part B of the figure shows how Q move is in the presence of an electric field E which is parallel to the bond axis. This charge is seen to move by an amount del R, which is equal to alpha parallel into E by Q, where alpha parallel is the polarizability measured along the bond axis, and, uh, and consequently the distances Ra and Rb changes by like changes by this relation, which is minus del Ra, which is equal to minus delta Ra, which is equal to delta Rb, which is equal to del R, which is equal to alpha parallel into E by Q. Part C of the figure shows how the, uh, how the bond charge moves when electric field is applied perpendicular to the bond axis. In this case, del R is equal to alpha perpendicular into E by Q. And to lowest order, the distance Ra and Rb changes by amounts like given by this. Delta Ra is equal to del R square by 2 Ra, which is equal to alpha perpendicular square E square divided by 2 Raq square. Similarly, delta Rb is also given here. Here we can see that if a field parallel to the bond axis can induce a linear change in the distances Ra and Rb, but a field perpendicular to the axis can induce only a second order change in these quantities. We can see that here. The quantitative predictions using the bond charge method. According to Phillips and Van Vechten, the linear bond polarizability can be is represented by this equation, which is alpha is equal to 1 by 3 whole multiplied by alpha parallel plus 2 alpha perpendicular, which is equal to 2a0 whole cube into d into e0 square by eg square. where A0 is the Bohr radius, which is 4 pi epsilon 0 h rho square by me square. E0 is the E0 is the Rydberg unit of energy, which is equal to me raised to 4 divided by 2 into 4 pi epsilon 0 whole square h cross square. And D is a numerical factor of the order of unity, and Eg is the mean energy gap associated with the bond. Eg can be represented by this equation, where Eh is the homopolar contribution given by Eh is 40D raised to minus 2.5, and C is the heteropolar contribution given by this equation. Here, here, Eh is measured in uh, electron volts and D is measured in Armstrong. And here the Za and Zb are the number of valence electrons on atoms A and B respectively, and e raised to minus kr is the Thomas Fermi screening factor with r is equal to half d, which is the bond length, half of the bond length. According to the bond charge model, the way a material reacts to light is influenced by how the bonds between its atoms can be distorted by an electric field. This distortion is represented by the bond dipole moment, which is expanded here. Since the bond charge model assumes that the bonds are axially symmetric, the only non-vanishing components of the hyperpolarizabilities are these ones. Here we assume that the bond axis is along Z. The present model obeys Kleinman symmetry since it does not consider the frequency dependence of any of the optical properties. Because of Kleinman symmetry, we can express beta perpendicular equivalent to dou alpha xx divided by dou alpha ex, as this beta perpendicular is equal to dou alpha x set by dou alpha dou ex, which vanishes as C perpendicular cannot produce a first order change in alpha ij. We also find that this quantity will be equivalent to 0. So the only non-vanishing components are beta parallel, and gamma perpendicular. Their values are given here. These equations provide the basis of the bond charge model. Quantities EH and C, which are given above, are EH and C, which are given here, are are developed in power series in the applied fields E parallel and E perpendicular through the use of equations given above here, which are given by the equation given here. This these three equations, and the hyperpolarizabilities can be extracted from the power series through the use of equation through the use of this equation. Finally, susceptibilities are determined by summing over all bonds in a unit volume, taking account of the orientation of each particular bond. This model has been shown to provide good predictive value. For instance, Kemla et al. Have found that this model produces almost 30% accuracy in calculating the third order non-linear optical response for germanium, silicon, and gallium arsenide.
So, the topic of today's discussion is the fascinating world of chiral media and the unique optical properties. Chirality, it is all about the intriguing dance of molecules and light. We'll begin with the basics and then we will dive into some cutting edge research in this field, and we'll see how it is still a field of great interest. So we will start with the chirality and the optical activity. First, let's understand the fundamentals. Okay, and chiral molecules. A chiral medium, it is a medium which is composed of chiral molecules. And a chiral molecule is a molecule in which the mirror image looks different than the molecule itself. That is how your chiral molecules are like, which are how your left hands and right hand are non-superimposable mirror images. So those are the chiral molecules. And we know that CH4, CO2, H2O, they are achiral molecules. But we have a lot of chiral molecules, which are, like, example is some organic molecules. So like the given molecule here, we can see. So, and we'll discuss that, we will see that chiral media, it display some remarkable property which we know as optical activity, which means that when linearly polarized light passes through these material, its plane of rotation rotates. And then we will look at like some important definitions regarding the optical media, regarding the optical activity of the chiral media, which means now we know that chiral media have optical activity, which means it rotates the plane of polarization. And we have dextro-rotatory material, in which the direction of polarization rotates in clockwise manner. And we have levororotatory materials, the materials in which the direction of polarization rotates in clockwise manner. And then we have some small important definitions, which are enantiomers and racemic mixtures. So enantiomers are a pair of molecules which are mirror images of each other. And the racemic mixture is when you mix equal amounts of two enantiomers. And there is the thing to notice is that in a racemic mixture cancel out the optical activity, resulting in no net rotation of the polarized light. Now we are discussing some non-linear optical properties. Okay, so now let's explore some non-linear optical properties of the chiral medium. While we know that these chiral molecules are isotropic, but they are also non-centrosymmetric, which enable them to possess a second order non-linear optical response. And this response allows them to produce, and this response allows for phenomena like sum or difference frequency generation. Unlike harmonic generation, which typically doesn't occur in chiral media, sum or difference frequency generation can be produced But here is a catch. It only happens if the two input beams are non-linear. As we all know what is a sum and frequency generators are. So sum frequency generation, it is a non-linear optical process where two input beams at different frequencies interact in a non-centrosymmetric medium to produce a new beam with frequency which is equal to the sum of the input frequencies. This process can occur in chiral media, but it requires the two input beams to be non-linear and non-collinear and orthogonally polarized, which we just discussed. And then we'll see that the theory of this non-linear optical properties in chiral media has a rich history. We have Geodemy, which studied this in 1965, and then we have Rentzipis, which studied this thing in 1966, and then we have Burbist, which studied this thing in 1999. So these all scientists have advanced our understanding of the topics. Now we are gonna see the theoretical description of the second order processor in chiral media. So we know that the second order polarization is shown by the formula here, whereas polarization is 2 nu naught summation of jk, chi, ijk, ej and fk. And we have and ejk represents frequency at omega 1, fk represents the field at frequency omega 2. So we have this. And then we are gonna see the final equation. It becomes like this, where the value of Sijk, Aijk is there. And then with this all leads to the coefficient Aijk, which determine the sum frequency generation in isotropic but centroposed, in isotropic but non-centrosymmetric media, the Sijk term vanishes and only the elements of Aijk left are A123, A231 and A312, which becomes equal, and our final non-linear polarization becomes this. So we see that now we will discuss how all this theory translates into the real world observation. There is a very fascinating example which involves arabinose, a sugar molecule, when illuminated by two input beams at different frequency of some frequency generation of 2314 Armstrong was reported. But when no signal, this phenomena was observed for both dextrorotatory and levorotatory forms of anabose. However, when the medium contained a racemic mixture of the two forms, no signal was detected. This supports the concept that the racemic mixture cancels out the optical activity. Now we will see the measuring of A123, which are the only coefficients left of Aijk, and how its significance. The value of A123, which plays a crucial role in some frequency generation, was measured using this experiment to be 1.3 into 10 raised to power minus 18 millivolt. And to put it in perspective, the value of quartz, a well-known material, was approximately 1.61 into 10 raised to power minus 17 millivolt. Finally, it's essential to know that ongoing research in this field is continuously revolving new insights into the non-linear optical properties of chiral media. Recent studies which are like represented by Belkin et al. Helps us understand the better and help us understand the better optical behaviors and how to control them. So in conclusion, the optical properties of chiral media are a captivating intersection of chemistry, physics, and our science. They not only deepen our understanding of the molecular world but also promise us the exciting applications in non-linear optics.
Hello everyone, myself Simranjit Kaur. So today we will discuss about liquid crystal materials and their remarkable nonlinear optical effects. These unique materials are composed of anisotropic molecules, which we'll discuss later. So liquid crystals have a distinctive feature. Their response to light isn't immediate. Instead, it unfolds over a longer time scale and often spanning milliseconds or even longer. Let me share my screen. Sure. Okay. So, yeah. So, in the next few minutes, we'll be exploring the fundamental principles that underlie their nonlinear optical effects. We'll dive into their various phases, including the isotropic and mesophases, and understand how they transition between these states. Along the way, we'll uncover their role in applications that demand a patient response. So talking about their unique phases, we have isotropic phase and mesop phase. Above a particular transition temperature, which varies among different liquid crystal materials, typically around 100 degrees Celsius, these substances exist in what's known as isotropic phase. So in isotropic phase, liquid crystals behave just like everyday liquids. Their molecules move randomly with no particular alignment or order. As temperature drops below the transition point, liquid crystals enter a mesotrophic phase. Here, something remarkable happens. The orientation of neighboring molecules become highly correlated. This newfound order gives rise to the name liquid crystal. This phase offers unique optical and electrical properties, which will be explored in greater detail. Uh, at even lower temperatures, liquid crystal materials undergo yet another phase transition. In this phase, they behave as ordinary solids with a highly ordered molecular arrangement. With Within the mesophase, different types of molecular order can emerge. Two of the most common are nematic phase and the chiral nematic phase, also known as cholesteric phase. In the nematic phase, the molecules align in the same general direction. However, there's no specific spatial arrangement. Think of it as a group of people pointing the same direction, but they're not arranged in any particular pattern. This order is relatively simple. The chiral nematic phase or the cholesteric phase offers a twist. Here, molecules not only align but also form a spiral or a helical pattern. This results in a beautiful and intrinsic structural order. Next, we'll focus on their behavior in the isotropic phase, revealing a fascinating non-linear response that is not only distinctive but also strongly temperature dependent. What makes this phenomenon particularly intriguing is that the magnitude of nonlinear response is not constant. It strongly depends on temperature. As the temperature changes, the nonlinear response of liquid crystals undergo remarkable variations, which scientists have extensively studied. In one specific case, uh, Hannison made a significant discovery regarding the nonlinear response of liquid crystals in isotropic phase. They found that two critical parameters, the nonlinear coefficient N2 and this one N2 and the response time tau, could be expressed in terms of specific equations. So talking about nonlinear coefficient n2 and the response time tau. So for this particular case, the nonlinear coefficient n2 was determined to have the value of this 2.5 into 10 to the minus 15 when the temperature is above the transition temperature T star, and the response time tau was found to be inversely proportional to the temperature and varied between the range of 1 to 72 nanoseconds for temperature between 130 and 80 degrees Celsius. So the significance of these findings is that they highlight the extraordinary potential of liquid crystals, not just in the mesophases but also in the isotropic phase. Liquid crystals' nonlinear optical properties, especially their temperature dependence, offer exciting prospects for diverse applications from advanced displays to optical devices in science and technology. So, uh, for the mesophase, what sets the mesophase apart is the mechanism at play. In this case, it's all about the collective orientation of many interacting molecules. Unlike the isotopic phase, where individual molecular orientation matters, in the mesophase, the the molecules align together in a coordinated fashion. This collective behavior amplifies the nonlinear response. The enhancement in nonlinear optical properties in the mesophase is truly remarkable. It's not just a modest improvement, but can be as much as 10 raised to the 9 times larger than that observed in other materials like carbon disulfide. This extraordinary amplification makes mesophase liquid crystals an invaluable resource for a wide range of optical applications. Uh, let, let us explore some experimental insights. When conducting experimental studies on nonlinear optical processes in nematic liquid crystals, one common practice is to anchor the molecules at the walls of the cell containing the liquid crystal material. So what's the purpose of anchoring? The anchoring serves several vital purposes. First is it provides a controlled environment for the liquid crystal molecules. By ensuring that molecules adhere to the walls, researchers can precise control over their orientation and alignment. This controlled alignment allows scientists to understand how the liquid crystal molecules react to external stimuli, such as an incident laser beam. Okay, so next we'll talk about analyzing liquid crystal responses, the theta plus theta naught angle, right? So in this analysis, we consider theta plus theta naught, where theta naught represents angle between the director, a vector indicating the average molecular alignment in the liquid crystal, and the propagation vector k of the laser beam in the absence of laser field. So theta represents the reorientation angle, indicating how the director's alignment changes under the influence of laser field. This angle is pivotal in understanding how liquid crystals behave when subjected to external influences, particularly laser beams. By examining how theta and theta naught change under the influence of laser field, researchers can gain insight into complex interplay of molecular orientations, which is essential for developing advanced optical devices and displays. Now, understanding the analytic equations of liquid crystals. So let's break down this equation. This K1, it signifies the elastic constant of the liquid crystal, capturing how it responds to the changes in orientation. And this NO and NE represent the ordinary and extraordinary refractive indices of the nematic liquid crystal when it's not influenced by an incident laser beam. This equation serves as a foundation for understanding how the director orientation of the liquid crystal changes in response to external stimuli, such as laser beam. To arrive at a meaningful insight, this equation needs to be solved while adhering to specific boundary conditions. These are input z equal to 0 and output z equal to z, planes of the cell. Ko and Sheen have taken this analytical procedure a step further and discovered that the director orientation typically takes a specific form. Moreover, this analysis has provided a means to calculate the change in refractive index average over the length of the cell. This can be expressed as delta n is equals to n2i, where n2 is determined by this equation, and under certain conditions such as d is equals to 100 and 100 micrometer and these given conditions, this calculations yields a value of n2 equal to n square equal to 5 into 10 plus minus 7 meter square per watt. In essence, this equation forms the backbone of our understanding of how liquid crystals interact with light and external forces, paving the way for the development of advanced optical technologies.